Hi, welcome to the next of our series of practical electromagnetics for engineers. We're going to be getting into something more about how the universe works, what electricity is. And because we don't get to control the laws of the universe, because we live in the universe and however it works is essentially made for us, we have to rely on a little bit more mathematics, a little bit more physics type stuff for this section of these videos. And so what I plan to do is to go into as much as I can how electricity is, although nobody really knows what electricity is at a deep level, which involves some mathematics, and I've chosen to include the mathematics in the video to develop them as I go along, rather than make a separate series of videos on mathematics that are unrelated to it, or steer you to some of the really excellent videos out there on basic stuff. Feel free to go look at those if you don't understand it. For those who know this, I apologize if this is a review, but I figure this is sort of a better way to do it than to do it separately. So Coulomb's law, what is it? Well, it's essentially given by this equation right here. It says the electric field, and that's this E, is given by this equation right here, and we'll get into what that is. Another part of Coulomb's law, essentially, is that the force on a charge, that's what this Q is proportional to the size of the electric field and the size of the charge. So what does this mean? Something called charges Q create electric fields, and the force on a charge in an electric field is proportional to the electric field itself and the size of the charge. And let's get into what that is later, but let's understand Coulomb first. It turns out that Charles Augustin Coulomb was born in the 18th century. He died early in the start of the 19th century. And he happened to be a military engineer who had fallen on hard times, and he couldn't buy his way into the Paris Academy of Sciences, the university he wanted to attend. So, because he was poor, the only way he could do this was to win some kind of major prize competition, and prize competitions were really popular at this time. And he essentially entered a contest to make a better compass, because compasses were how ships navigated, naval power was the thing at that time, and so this was essentially a military prize. He basically did this by hanging things from a very thin thread and measuring how much they rotated, and it turned out he had the best device for measuring small forces in the world. It turns out that even, hundreds of years ago, he could measure forces as small as about 2.5 billionths of a gram with this thing. And it turned out this thing was so sensitive, it was affected by small electrical charges and static on dry, wintry days. So he used it to measure the force between electrical charges, and that's what he happens to be remembered for. His device itself looks like this, and you can find the pictures online. Both of these pictures are from Wikipedia. And so he's either remembered fondly or cursed by students for hundreds of years because he needed money to go to school. So looking at Coulomb's law, the first thing we noticed, the first thing I want to talk about, is that a lot of these quantities have arrows above them. An arrow above a variable it basically means that variable is a vector. So most of you know all of this. But let's go into vectors. Now, a vector is a particular type of number that we use when we need to represent both a quantity of something, an amount, which is what numbers are usually and math is usually used for, but also a direction. So if this point out here, let's call it point A, if we want to know the direction from the origin, which is right there, we know at some certain distance the line just traveled. But we know it also has an x component to the distance, right? It's this much along the x, and let's call that x naught. It's also this much along the y component. We call it y naught. So we represent this point as having two coordinates. It turns out in three-dimensional space, we need to include a z component as well. But because I can't draw well in 3 dimensions, certainly also not while I'm recording a video, we're essentially going to ignore the z direction as I explain stuff, but all the stuff we do applies to that z direction. We'll bring it back in occasionally just to remind you of it. So how do we represent this vector? Well, some people do it just by giving the set of coordinates. They'll write x naught, which is the amount, here along the x direction, that distance along x, comma, y naught. A better way to do it is to say the vector A, right, essentially is equal to x naught, and we use the x direction by something called a unit vector we called x hat there, plus y naught, the amount along y, with a unit vector along the y direction. Let's go into these unit vectors for a little bit, because these are actually pretty important. And by the way, this is the way we're going to represent vectors throughout this video. So unit vectors essentially depend on something called orthogonality. And orthogonality means that the axes are completely independent from each other. So the y-axis and the x-axis, for example, don't affect each other. And the z-axis as well, if we're working in 3 dimensions, doesn't affect each other. So our unit vector in x has a length of 1 along x, the unit vector in y, and so let's label that x hat. The unit vector in y has a length of 1 along the y direction. We'll label that hat. And the unit vector z has a length of 1 along the z direction. Why are they 1? Because if we multiply anything by 1, we get itself. And so multiplying by a unit vector doesn't change the value of a number. It turns out that if we were to have a point here, and it moved in x, its y position and z position are not affected at all. The x direction, an orthogonal set of axes, a system that has orthogonality, in fact, these 3 elements are completely independent of each other because the axes are 90 degrees apart. Now, this doesn't seem like much. It seems obvious, but it's actually really, really important. You know, we could draw, for example, a coordinate axis. Let's get rid of our z-axis there to give ourselves some room, and we'll go ahead and erase some of this stuff as well. But we could draw ourselves a coordinate axis such as the one that appeared here, that's not orthogonal. And let's put an orthogonal axis in there just so we know. So notice if I rotate the y-axis some amount theta degrees out of orthogonality, now if I move something in this direction along the x-axis, instead of it being absolutely independent of y, it's essentially moved a long way along the y-axis as well. So non-orthogonal axes, essentially, if you change a coordinate of one, you change the coordinate of the other. Here, if the axes are orthogonal, then it doesn't matter. I can completely shift something in x without affecting y. Why is this important? When we get to the future and we have some equation, f of x, comma y, comma z, in the x direction, plus some other equation, g of x, comma y, comma z, in the y direction, these are completely separate equations. Just like the real and imaginary parts in a complex number are completely separate, if you're in an orthogonal system, each vector or each complex vector, if it's represented by an equation, is essentially completely independent of the other ones. So this leads to a couple of questions. And a couple of things we need to know. The first question is, where do we put the center, the origin of these vector systems? I'm putting them in a particular space and drawing vectors relative to them, but it turns out actually that you might have a problem where you think, gee, it's in the wrong place. How can I put the center exactly where I want? Well, it turns out it doesn't matter where you put the center. This is something called translational symmetry. And translational symmetry means that for real physical laws, you can set this coordinate axis, the position of it, wherever you want. And all this means is that if we perform an experiment at one place and then we move to a different place, we should get the same results, which is pretty much common sense. For the same thing, you have rotational symmetry. It doesn't matter where you rotate the axis and point x or y to. So you're welcome, and this is a trick to solving electromagnetic problems. You're allowed to put this axis system wherever you want and rotate it along whatever direction you want to make the problem easier. The results will be absolutely the same. So what we see in Coulomb's law here is that we have two vectors that are subtracted from one another. So let's understand what a subtraction of vectors means. And let's take a really easy case. Let's just say we've got the y unit vector minus the x unit vector. And so one might think that the y unit vector, which is pointing here, and has the value of 0 along x plus 1 along y. And the x unit vector here, and let's subtract that, has the value of 1 along x and 0 along y. That this y minus x is going to point from y to x. So let's do our subtraction problem and see what we get. Essentially we get 0 minus 1, so minus 1 x plus 1 minus 0 y, 1 y. And if we plot that vector, rather than get a vector that goes down in this direction, we get one that goes negative 1 that way, 1 that way. So we get a vector that goes up that way. So this is a little strange. Essentially what it means is that if you have vector A and vector B, if you want to go from this point A to this point B, you do not write A minus B. That's wrong. It turns out you write B minus A. So that's a little counterintuitive, but this is how we subtract vectors. Where you're coming from goes at the end, where you're going to goes at the beginning. Little counterintuitive, now you know it, it's easy to remember. Another thing we might want to know is how long is this vector C that goes from A to B. So let's write our equation here. C is equal to B minus A. It turns out that the length of C is something called the magnitude. And the magnitude of a vector, and let's write basically C equals Cx, which is just some number for how long it is in the x direction. And we'll write our unit vector there, plus the, let's write this the correct way, that would make life a little bit easier. The y length of C along the y direction. If we want to know how long it is, we call that the magnitude of the vector C, and we represent the magnitude by these two vertical lines here. That's just equal to the square root of Cx, the amount along the x direction squared, plus Cy along the y direction squared. And so this is the magnitude of a vector here. One of the things you need to remember, along with the fact that when you subtract vectors, where you come from is subtracted from where you're going to. And that's all we're going to say about vectors for the time being. And the reason we need to know that is that we're doing subtraction of vectors here, and you see this part down here in the bottom of Coulomb's law is a magnitude. So this is not a vector. Anything inside the magnitude sign is a number. It's simply the length of the vector. Okay, so we've done a pretty good job of explaining a lot of Coulomb's law so far, at least some of the math behind it. Let's move on and look at another part, which is Q, which is the amount of charge that gives rise to the electric field. This gets a little bit complicated. What do we know about Coulomb's law so far? If we look at this, well, we know that we have two vectors, Rm and Rq, and I've chosen those names myself, where Rq is the position of the charge, and Rm is the point we're measuring at. And I'm going to, because of translational symmetry, set Rq equal to 0 by putting the charge, Q, down here right at the origin. Then the length of Q becomes 0, and we can get rid of those two vectors, and then we can write Coulomb's law this way. It turns out that when we do this, we see that Coulomb's law generates a vector. Because the electric field is a vector, so we're going to be generating vectors. That vector points in the direction of where we're measuring to. So if we want to measure at some point m out here, essentially we have an electric field, or the electric field vector, pointing out away from the charge. That's what this says right here. And we know that it scales by the length, the inversely to the cube of the length of this vector. And we'll look more at that scaling a little bit later. But the important thing to note is that the whole thing that generates this electric field is the charge. And Q is the amount of charge. If you have more charge, you double the charge, make QA twice as big, you get 2 times the electric field. If you make QA 10 times as big, you're going to get 10 times the electric field. The electric field scales with the amount of charge. But what is charge? Well, now we need to look at another part of Coulomb's law, which is this force term. And let's say we've got another charge, Q sub b, and it's sitting out here at this point, M. What's going on with this? It turns out that this Q sub b, this other little charge here, is going to feel a force. The force is a vector. It points in the direction of the electric field, which is away, and the size of that force is proportional to how big that second charge is times the size of the electric field, which in turn we know is just proportional to QA. So what does this mean? There's a lot of math this gets quite complicated, but in a really simple sense, what this means is charges put out force fields. Invisible force rays is the thing I like to call them. We call these invisible force rays generated by charges the electric field, and we give it the variable E, and we make it a vector because these forces push other charges in a particular direction. They only push on other charges. If something comes along here that doesn't have a charge, QB is equal to 0, the force is also equal to 0. So charges are things that only push on other charges. You may think, well, this seems kind of strange because my body's made of charges and I don't feel electric fields even though I've heard they surround me all the time. Well, it turns out that matter is composed of an equal number of positive and negative charges, so our bodies are continually being pushed and pulled the same amount by any electric fields they encounter, so the net force we feel is 0. So again, charges generate electric fields, these invisible force rays. So if you have a charge, it's putting these invisible force rays out in all directions. These invisible force rays only push on other charges. Other things don't feel them. It's very analogous to gravity, for example, where mass generates gravity, and gravity only affects things that have mass in a general sense. That's sort of doing a little bit of hand-waving, but that's the general idea. Electric forces are much stronger than gravity, it turns out, if you do the calculations. So charge is what generates electric fields. Electric fields are the invisible force rays that push on charges. If we also think about a charge right there at some point in space, this charge Q generates an electric field. We know that electric field has a direction given by a vector that has a length and a direction, which is simply the point the vector is at, r sub q, and so this point in space right here where I've drawn that is pointed at, let's draw our set of coordinate axes here, by the vector r sub q, and we know the electric field at some point r sub m, so let's write r sub m to represent that point, essentially, is proportional to the difference between these vectors, in other words, that way, divided by the magnitude, the length of those vectors cubed. What this essentially does is it creates what's called a vector field. At every point in space, every value of r sub m that we can possibly map to, there's an electric field. At this point in space, Coulomb's law says the electric field points out that way. At this point in space, it points away from the charge out that way. At this point in space, it's going to be very, very big because look, this distance between these two charges is small, and it scales inversely as the distance cubed divided by the vector, which turns out to be the distance square, as we'll see in a little bit. So the electric field at that point in space is going to be huge. Here, you've got something pointing away from the charge, and so on and so forth. This is a general idea, and Coulomb's law is something that creates what's called a vector field. Things that create vector fields map vectors onto every single point of space. So no matter where you are, this charge is creating a vector field which says the force another charge is going to feel, if you know the size of the other charge. A vector field is an equation Coulomb's law that maps a vector onto every single point of space. If you go into MATLAB, the computer program I prefer to use, you can actually get MATLAB to calculate vector fields for you and plot what it really looks like, where the longer the vector, the larger the electric field, and I've given you the code I used in MATLAB. It's only 5 lines long here to do this, but this is what happens when you have a computer program plot that vector field out for you, because doing this by hand and calculating at a lot of points would be very, very tedious to do. And it turns out you never see this when you get a homework assignment because it would just be too boring. But this is what charges really do, and so we don't talk about it very much because it's hard to do except with a computer. But with a computer, it's very easy to actually plot and map a vector field for a charge. So the Q of the charge would be right there with the vectors pointing out from it. So, what have we figured out from Coulomb's law? We know we have an electric field. At each point in space, this vector r sub m basically says at any point in space I can point to with a vector r sub m where I'm measuring the electric field, we create a vector. That vector, the size of the electric field, the invisible force rays, is proportional to the charge. We know it points in a direction that goes from the charge out to away from the measurement point because of this subtraction. So this is a vector that has a length of how far the measurement point is from the charge. And we know we also have a distance because there's the magnitude cubed in the denominator. So basically this is basically length 1 up here, or to the first power, length to the third power down there. As we see, that's inverse square. But we have some terms we haven't explained down here, 4 pi and epsilon. Let's take a look at the 4 pi right now and see where that comes from. So here's the equation that I just wrote up here. So I'm basically just going to copy this down here, but let's do some math to it. Let's basically put the charge at the origin, which makes the position 0, which I'm allowed to do through translational symmetry. That simplifies Coulomb's law over to this equation right here. It makes it easy. And now we've got a vector that has a direction and magnitude divided by the magnitude of that vector cubed. If I turn this and say, let's just write this as the length of the vector out, oops, let's make this a real length. That's not a very good length. I'm trying to draw parentheses. The length of the vector in the direction, a unit vector from where the charge is out to where we're measuring. In other words, here's the charge right here, and here's a point out here where we're trying to measure. So our vector r sub m goes from the charge out to where we're measuring. We can write that as the magnitude of that times a unit vector pointing in that direction, because we know our idea of unit vectors. This cancels out of the numerator. This cube in the denominator turns to a square. And so I'm ending up, if I move my 4 pi around, with this equation right here. And now we see something interesting. We see in the denominator 4 pi r squared, where this is what I'm calling r is the magnitude of the length of the vector squared. We recognize this as the area of a sphere is 4 pi r squared. So why does that make sense? Where does this 4 pi come from? Let's take a look at a charge, Q. And we know this charge, the way I like to think about it, is putting all these invisible force rays out in all directions like a porcupine. If I draw a sphere around this charge, like that, and pick some area, and I'm going to basically choose this, and I'm going to say this has an area equal to 1. Doesn't matter what unit it is, I'm just going to set it to 1. Or I could set it to 10, it doesn't matter. You'll notice that this is just big enough for all these force rays to go through. There's a certain density or flux of force rays that goes through that area. But if I draw a bigger sphere, and let's call this radius r here, that's how big the radius of the sphere is. If I draw a second sphere and still keep my area to be 1, you'll notice that some of the force rays now miss. They don't go through the area. And if I draw still a third bigger sphere, and now notice my radius of this third sphere, R3, has increased, even more of the force rays don't go through that area. What this means is that the number of force rays per unit area scales as the size of this divided by the area of the sphere, because I know all my force rays are going to go through that sphere somewhere. And this is a general case of what we call an inverse squared law, things that scale inversely with the distance square, where r is the distance away from the thing that's happening. And we'll see this law over and over again, this inverse square law. But that's what this form of 4 pi down here in Coulomb's law means, is it means that the charge puts off this whole host of invisible force rays. The invisible force rays go out and they spread out as they move away from the charge, and so the number that go through any unit area drops off inversely as the square of the distance. What this means is if there's another charge, let's call it QB out here, it's going to feel a force. But that force drops off as the square. So if it's 1 unit away, it feels a force of 1 over 1, or 1. If it's 2 units away, it drops off as 1 over 2 squared, or 4. If it's 3 units away, it's a 9th. If it's 4 units away, a 16th. And so essentially what this inverse square means is that things have to be pretty close to a charge in order to feel much of the invisible force ray. If it's far away, it doesn't feel very much force at all. So let's wrap this all up. Let's summarize this. We have a charge that creates something we call an electric field, which is invisible force rays. Those invisible force rays, this electric field, essentially create forces on other charges. If something doesn't have a charge, the electric field doesn't affect it. Okay? There's no force on it unless it's another charge. The electric field itself points away from the charge. That's what the subtraction of vectors means. And it drops off inversely as the square of the distance, because they have one distance here and distance cubed in the bottom, so it drops off as r squared. The 4 pi is there because 4 pi r squared is the radius of the sphere, and we have this inverse dependence on distance squared, as we've seen. The only other piece that's left is epsilon. And epsilon is something called the permittivity, and it's just a constant that scales this equation so that everything works out in terms of the values. It happens to be a very, very small number, and we'll learn more about it later. But epsilon is just the constant at this point in time that keeps all these equations balanced so the units work out, so the forces are actually correct in what we measure. So to wrap up, charges create invisible force rays. They map an invisible force ray to every point in space, creating a vector field. These invisible force rays only push on other charges, and because invisible force rays sounds pretty silly, we happen to call it the electric field, because that sounds much more mysterious to those who aren't initiated into the brotherhood of electrical engineering.